What?
You were in last day?
Yeah, I had a doctor's appointment.
Oh, okay. You coming in Wednesday?
Hey, I got this part right. I was so scared I was gonna get that wrong.
Well, I didn't check for accuracy.
Oh, never mind. Okay. 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 Just kidding. Just kidding.
But I can certainly look at it.
Oh.
And then these have different neutrons. You could pick like nitrogen or boron or something.
So it's partially right. Okay. I can work with that.
Yeah, same thing with these ones. Nucleon refers to proton neutrons, so you could do like boron 12 or nitrogen 12.
What is, how do I figure out the bottom row?
On the bottom one is just like pick your favorite, whatever.
What if I don't have a, what if I don't have any of them?
You know, like gold or something?
I don't know. The one that's coffee.
Yeah, but she was looking for an element.
Yeah.
Okay, Michael. Okay.
Because I thought his name was Asher. That his name was Asher? No, I thought the Michael's name was Asher. Oh. This is so off. Or whatever paper has my name on it.
Huh?
He would tell us what the rest of it is. Yeah.
And he doesn't have answers from. I haven't seen one that I haven't. Anyone is
Yeah.
So would I do that? I don't feel.
Yeah, because they should say the same thing, because like, one of them out there. Yeah. Well, it's not sure the same thing, like, and then, you know, they should be doing, over Richard things, and then you might go have a decimal point, if you want to put a decimal point, I don't want to do the addition, that's what I'm thinking. So I have to draw it out more explicitly. All right, let's go ahead and get started. So I have a fat stack of papers, so I'll be trying to give this out to you while you work today. Let's see, I'm trying to think. Any questions before we get started? So just putting it on your radar, so don't forget we're on week 4 right now. And so next week we have our exam in class, and my plan for that is probably do some review on Monday and then exam on Wednesday. So that's on your radar. Any questions about anything? Yeah, so exams are going to be open note, especially for my 104 class. So yeah, that will be that. I say that I typically write them for like an hour period, and then you get like all of Wednesday to work on it, so lecture plus recitation. And if it takes you longer, I mean, there's no one after us, so you could stay. I don't remember if people have like time accommodations, but You don't have to go to the testing center for that. You can just like stay here. I'm not trying to make it like a time pressure exam. Other questions about the exam? Yeah, we'll go over it. And then typically I've done like exam corrections too for the midterm. Because sometimes I write, at least traditionally I've given out kind of like trickier exams that are not a lot of multiple choice, but a lot of like working through stuff. All right, so let's talk about covalent bonding. Again, if you have questions, ask questions. Always ask. And so now covalent bonding. And so we'll look at what makes a covalent bond. And the distinction, of course, with the covalent bond is now electrons are shared between atoms, and they are called bonding pairs. So again, just kind of, put a little recall. So we said, right, ionic was a transfer. And i.e., we can make a little example. So we made, right, sodium plus and chloride ions. So one, again, actually transferred. But now we're not doing that, so now we're getting sharing. And so let's look at this water picture here. And so let's also look at how we kind of approach these drawings. So you want to start with your Lewis dot structure of oxygen. So what does that look like? And to make sure you draw it correctly, again, I don't check your homework for accuracy. At least try to glance through. If I see anything like super egregious, I'll try to write some notes, especially with these Lewis dot structures. But remember our oxygen, and let's just write our electron configuration while we're here. So start at helium, 2s2, 2p4. We can rewrite this. So right now we're just kind of recapping. So remember how you fill in that p orbital. So we have 6 valence electrons total, right? 2 in the s, 4 in the p. And that should match, again, with your numbers. So just, again, double check your sanity. Sorry, looking for my periodic table. Oh, no. Let me pull a periodic table. Now, where's the periodic table when you need one? Seriously? There we go, sorry. So again, I'm just emphasizing, right, oxygen group 6, 6 valence electrons, so we're all on the same page here. And then we want to fill in that p orbital. Remember, 1 in each p, so we have 4 in the p, so 1, 2, 3, 4. Then we want to draw our Lewis dot structure to look like that, so 2 dots on one side. Again, looking like this now. And then these 1 lone electrons hanging out. So there's our Lewis dot structure. And so we can also start to kind of label things here. And so notice we have our lone pairs on oxygen. And so often we draw those little kind of ears around them. And so these are electrons that are typically not involved in bonding. Again, they're paired, so that usually is an indication that they're not involved. And then they do occupy space, so we'll look at kind of geometry. And so, of course, right, this electron then, those are primed for bonding. And so we had hinted at that previously, where we said, well, now I can look at this Lewis dot structure. I can say This wants to make 2 bonds. So that matches right with what we expect for our formula for H2O. And so now I'm going to kind of redraw this for clarity. And so I'm just going to redraw oxygen with blue. And then now we're going to tack on hydrogen. And so again, right, we can think about hydrogen. So if I put hydrogen off to the side, so of course, right, this is its Lewis dot structure, group 1, 1 valence electron. And so we know this electron is going to be involved in bonding. And so it would bond like so. And so notice, this is also considered just a normal bond. And so normal just indicates that each atom is contributing 1 electron to that covalent bond. And so now we can say, right, this is our bonding pair. And now I'm just going to redraw this. So of course, typically we don't show the electrons when we kind of make a bond. So more commonly, we just write it. So oxygen, again with our lone pairs. And then we just draw a line then to show that we have a bond then with our hydrogen. And so here I am trying to show 3D geometry. We're going to kind of start dancing around the subject of geometry, only because it's a good time to introduce it. And again, notice, right, these lone pairs are taking up space. So that kind of forces these hydrogen down into that bent structure that we see. Questions so far? And so now we can look at the diatomic molecules. And so right away we can kind of see why hydrogen and then like fluorine, chlorine, bromine are diatomic. So of course their Lewis dot structure is just 1 electron. And then we can put them together. And so I'm just going to use this other notation just to show you another way to draw things. So this is half arrow notation. So just showing the movement of 1 electron there. And so that would create a bond. And so again, right now we just have a nonpolar bond. So again, 1 line shows those 2 electrons. So now fluorine, we can do the same sort of thing. So start, right, with its Lewis dot structure. So we have fluorine, right, 7 valence electrons, so it's in group 7. Put some notes, right, 7 valence electrons here. And then again, note, we just have that 1 little awkward electron. So we could call all of these, right, lone pairs. So fluorine has 3 lone pairs on it, how it's drawn. And now this, right, wants at least typically 1 bond. And so then for our diatomics, this is why fluorine bonds with itself. And then again, each fluorine has 3 lone pairs on it. And so then the other thing you want to do is kind of analyze this structure. So these structures, you know, they may seem elementary, but you can get a lot of information from them. You're going to be able to determine geometry that helps you determine, again, the different properties. And so then we want to count how many electrons each fluorine feels. And so if we look, I kind of use this highlighter. So of course it's feeling the 3 lone pairs on it. So 1, 2, 3, 4, 5, 6. And then it's feeling, right, these shared electrons. So that means that it feels 8. And we use that term, kind of feels 8, just what is it being satisfied by? So yes, octet rule. Then we can do the same analysis for this other fluorine. And of course, write 3 lone pairs plus that shared bonding pair, so that again, this one also feels 8. So that's all satisfied. So let's look at some more. So what happens if we try oxygen out? So try it on your own for a second. What does oxygen look like? What do you think its Lewis dot structure looks like as a diatomic? Does someone want to put this on the board for us? Now that I said it, I don't know that there are markers. Okay, this one's at least somewhat functional. Someone want to throw it on the board for us? What do we think? Ethan, you want to put it on the board? It looked good from what I, unless I was completely off. But anywhere you want. Well, let's see what you got, even if it turns out wrong. But I thought you did it. Excellent. So that looks good. So did we all get something that looks roughly like that? And so again, you could have started with your Lewis dot structure of oxygen. And then I'm not sure how you approached it, but right away, right when I look at it, I see, oh, okay, it probably wants 2 bonds. You could also start off, trying to draw just like a structure. But then when you draw these, the most important part is, well, how many total electrons do I have in this party? And so you can add up all your valence electrons. So oxygen, each one brings 6. So 6 times 2 gives you 12 total. And so that's how you could start playing it around. So 1, 2, 3, 4, 5, 6, 7, 8, and then you could maybe see that, or, you know, if you kind of got there through another permutation, that's also fine, because you could play with it, right? And then just start to see, well, if I don't have enough electrons, I'm going to have to move one over or something. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 total electrons, 2 bonds, like again, you could predict. And then again, make sure that they are satisfied then. So this oxygen, oops, right, feels 8. So 1, 2, 3, 4, 5, 6, 7, 8. So it's satisfied by the octet rule. Same with the other ones, so they're identical. So again, just kind of do a sanity check. Yep, feels 8, looks good. So then let's try our last diatomic. And so see if you can draw nitrogen then. So I'll give you all like a minute or so. So somebody tell me, what does their nitrogen look like? How many lines between them? 3. So that sounds good. Is that what everybody got? So nitrogen, we could start with our Lewis dot structure. And so there's kind of our hint, right? 1, 2, 3. So it probably wants to make 3 bonds. And then we could also see, well, if there's 2 nitrogens, right, each of them has 5 valence electrons times 2, so we have 10 total to work with. So we're kind of limited. And so again, if you started kind of playing with them, you probably saw we need 1 on the end, and then again, yeah, 3 in between. And then each line, right, is 2 electrons. So just make sure we're all clear on that. And so it is kind of a game of guess and check, right? So there's no wrong starting point. So again, you can always just start, right, make a line. So 1, 2, and then that's where you kind of have to play with it. So right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, you could draw it like that, right? But then right away you start to see, well, there's no octet rule satisfied. So that's where you can see maybe if I move these to the middle, that helps us out. So does that kind of make sense? Like there's no wrong way to start these structures. You just have to make sure how many total electrons do I have to play with and how might they form. And then I'm trying to get y'all to kind of see these patterns so that you can kind of recognize, oh, this one will probably make 3 bonds or 2 bonds, and go from there. But we'll keep playing with it. And so now let's figure out, well, how do we even predict what type of bond? Is it ionic, covalent, polar covalent? What is that? And so we have different ways of kind of calculating this. And so one way is also based on the electronegativities. So if you recall, right, last week we talked about electronegativity, and we said that was the pull that an atom has right in a bond. So don't forget that. So that was right in a bond. And so again, fluorine is the most electronegative, so it really wants to fill up its octet like we discussed. And so what can we do with these electronegativities? And so on an exam, right, I would have to provide you this chart or the values. But then there's kind of this correlation. And so this is not all encompassing. So bonding is kind of like a continuum of bond types. And especially if you get sometimes you can get out in this like weird range between polar covalent and ionic. And, you know, sometimes there's like research areas of interest there. But for our purpose, we either mainly care about kind of 2 different things. And that's really establishing their difference in electronegativity. And right, so ionic, let's just recap. So again, we said that was metal plus nonmetal. So that's going to be, again, for our purposes, kind of the first indication of what type of bond this is. And now let's do the math on this. Let's calculate it. So it says that this is an ionic bond is brought on between a very large difference in electronegativity, so larger than 2 plus. And so let's go through that calculation for sodium chloride. And again, right, you have to get these values from a chart or other sort of reference table. And so if we're doing sodium chloride, we just need to take the difference. And so we can look up, so chloride is 3.16. And then minus, so sodium is 0.93. So just taking the difference. And then we got greater than 2, which is about what we were expecting, right, for the ionic compound. So I'll just write out the work here. That was like not clear what I'm doing. So sodium 0.93, and we took the difference. And then got 2.23. So that's just our difference in electronegativity values. And so we're just verifying, yes, that's ionic. And so now what about this distinction between polar and polar covalent? And so this can be kind of trickier, and we'll talk about like why we care. But first we want to identify, well, is our bond, is it mainly covalent? And so sometimes this is also called completely nonpolar covalent bond. And well, let's look at that extreme. And so this extreme, when their electrons are shared equally, is of course due to a very small difference in electronegativity. So this could be generally due to, right, the same atom. So AKA, right, all our diatomics fit under this. So any diatomic would then be a purely nonpolar covalent bond. But then as we start to get into other compounds and making different covalent bonds, then we may have what's called this polar covalent bond. And so now we have uneven sharing of electrons, again, going back to that electronegativity. So how much, right, is that other atom kind of pulling the electrons towards it, and then, of course, making it have this bigger cloud. And so that's also what this shape and cloud is showing us, right? So these are all just electron density probability maps. So if this one is larger, it's saying, right, the electron is mainly concentrated on this atom here. So this might be HCl or something hiding in here. And so let's do the calculation for HCl. So we said chlorine was 3.16 previously. And then we get hydrogen. So hydrogen is 2.1. I'll be lazy. And so we get about a difference of 106 in electron negativity. And so again, based off of our scale, anytime it's greater than 0.4, that's already considered polar. So of course you would have different varying degrees of polarity. And that also affects kind of your different characteristics. So the more polar, then that can lead to different properties, as we'll kind of continue. And so again, right, it's just a continuum of bonding, and you can get into weird bond lengths, so kind of anything long as well. But that's just the basic gist here. Questions about this part? All right, and now this is just kind of going over what we call these bonds. So of course, if we call this a single covalent bond, that's just referring to two electrons being shared, again, with that one line. And then again, notice some terminology. So, right, hydrogen and helium satisfy the duet rules. So again, when you're kind of double checking, is my structure reasonable? You're also seeing, right, hydrogen only has two, so that's good. And right, you wouldn't want hydrogen to have 8 or something crazy, and then you might want to reevaluate your structure. And so like we saw with oxygen, so you all figured that out, and then we would formally have a double bond. So they use the term double covalent. People just say, right, double bond, triple bond. So double bond, sharing 2 pairs of electrons, aka, right, 4 electrons total. So again, we don't normally draw out all 4 explicitly. And then it mentions elements that can typically double bond. And again, we'll look at those, but we'll keep kind of talk about these different compounds. Of course, carbon, right, carbon-based life, so carbon can do all sorts of bonds. Nitrogen, you know it wants to make at least 3, so of course it might be able to do some funky combinations too. So same thing, oxygen, sulfur, they want to make 2 bonds, so they could definitely do some double bonding like so. This is kind of typical for oxygen. And then these R's just signify like any organic group on there, whatever, chain, or they could be terminal. And then just triple bond or triple covalent bond. So again, 6 electrons, 3 lines to symbolize them. And it bothers me that they drew it like that, but whatever. And so again, we'll kind of see the triple bonding with especially carbon, nitrogen, and some funky other stuff. All right, so now we're going to look through the different groups again. and kind of see the typical compounds that they kind of make, the geometries. And so before we start, I'm going to pass out this Vesper kind of cheat sheet shaped handout. All right, so we'll look at how to read this. But basically, I want to start off with group 4, and then we can hit up kind of other weird things. And so I just handed you this chart, and it is useful. So I wanted to at least kind of start introducing a little bit of shapes while we talk about trying to draw this, because they go really nicely together, hand in hand. And so the first thing you want to do is kind of look at this little key here, and it's got this 2, 3, 4, 5, 6. And so those big numbers there correspond to like how many things are attached to it. And so what that means, so let's just start off with an example. So now I'm looking kind of group 4. And so let's just start off with methane. So that's a pretty typical compound. And so if we're looking at our chart to help us, we can see, well, 4, because it has 4 things attached to it. So it doesn't have any lone pairs. And so you might have to start off with the kind of flat structure first. So this all depends on your level. So start off with, well, how many electrons do I have? So 4 valence electrons from carbon plus 1 from each hydrogen. So times 4, so we have 8 to play with in our system. And so then we can draw it out. So I'm going to actually draw it in 3D. So it should look something like this. And then I did draw the 3D structure. So this little wedge that's coming out. So this is still just 2 electrons, but I'm trying to show that it's coming out of the plane of the board. And then so these 2 hydrogens are in the plane of the board. And then the dash shows that hydrogen behind the plane of the board. So this gives us our tetrahedral structure here. So we can at least name that. So tetrahedral. And then, again, we'll be kind of looking at it, but you can see how we got to tetrahedral. So if you follow the 4 electron pair group, so since again 4 things attached to it, and then if you go over, so then it has 4 BP on the bottom. That just means how many like actual atoms, so bonding pairs. So that means it's attached to 4 things, and so we know that it's tetrahedral. And then we find a lot of group 4 tends to follow this, so it makes a lot of these tetrahedral complexes. And so, silicon tetrachloride, germanium tetrabromide. You could go crazy. So all these, make tetrahedral structures, so like chloroform as well. And so again, they're all going to follow that same kind of tetrahedral pattern. So of course, just note for like silicon tetrachloride, you want to fill in all your lone pair electrons. So all our lone pairs on chlorine that are non-bonding, we want to draw them all out. And so this should match with the correct total number of electrons. So silicon has 4 plus 7 times 4, so that should be, what, 32, right? So 32 electrons, and we can see each one of these branches is 8, so 8 times 4 gives us 32, so that looks good there. And so then other things that group 4 can do, so we see it mainly likes tetrahedral. But then I'd shown you, right, carbon can make some double bonds, for example. This is formate here. And so now let's look at its geometry. And so now, how many things are attached to it? To this carbon, so just think simply. 3, right? So it has just 3 things attached. So that would be 3 bonding pairs. So notice this structure, if you're following along with kind of like your cheat sheet. So now it falls under the 3 group. So 3 things attached to it. And again, this could be either atoms or lone pairs. So in this case, we're just looking at atoms right now. And then so I'm at my 3. I go over to 3 bonding pairs, because again, 3 atoms are attached to it. And so according to our chart, what's our geometry here? You can read the little, what does it say?
Trigonal?
Yeah, trigonal what?
Trigonal. Pyramid.
It's not pyramidal. What does it say? So trigonal, I know they're kind of hard to read. Planar. Yeah, so the geometry is trigonal planar. And so this is really important. So now this is telling us, right, this is actually a flat structure. So that's pretty cool. And again, compare that to our 3D. I should have brought in some molecules. All right, we have our tetrahedral structure in 3D versus now a planar structure. So that's telling us differences in kind of reactivity and how it can interact with different substances. So again, just trying to give you a 3D view of it, of silicon tetrachloride.
So one of the dashes is like a filled-in triangle and one is slashes. So two of them need to be different.
So, sorry, what was your question? I just didn't follow.
So like, the different way you're drawing the bonds now, one is filled in and one is a dash.
Oh, yeah, so you're talking about here. Yeah, so I did that for the tetrahedral structure to kind of show the in and out of the plane of the board. So just like this is drawn, right, so this is going out of the plane of the board, this is behind the plane of the board. And then this one, I didn't draw any like wedges or dashes since it's all in the plane, so it's in that paper plane. So that's fine, how it's drawn like that. All right, let's look at group 5, unless there are questions. So definitely ask questions. So now if we go to group 5, so how many bonds does group 5 typically want to make? What do we say? What do we think? Or even what are some classic, maybe group 5 compounds? If you had lab today, you have an advantage. You're trying to detect one of them. So how many bonds do they make? Any thoughts? You can at least write up nitrogen for some inspiration. So write nitrogen, group 5, 5 valence electrons. So how many bonds does it want to make usually? Yeah, 3. So it can do 5, but we'll talk about that later because it's more like expanded octets. So normally, right, it just wants to at least start off with 3 bonds, but then we'll talk about how else it can react. And so our classic compound for this is always ammonia. And so now let's just draw ammonia. And so again, add your electrons up. So write 5 electrons from nitrogen, 1 from each hydrogen, so 8 electrons on there. I'm not drawing 3D right now. And so now let's figure out what group it's in. And so this is where we do have to count the lone pair. So now the lone pair counts as a group it's attached to. So it has 1, 2, 3, 4 things again. So it's group 4 here. So 4 electron pairs. And then we go over. Well, it's not tetrahedral, right? Because it doesn't have 4 things attached to it. But then if we go 1 over, well, it has 3 atoms, right? And then 1 non-bonding pair. So that's what's shown in your little key. So your little key calls it, right, 3 bonding pairs, 1 lone pair. So that's what that LPBP stands for. And so what geometry is this then, according to our little chart? We can read it. So what do we see?
Trigonal pyramidal.
Yeah. So trigonal, pyramidal, or pyramidal. And so again, right, this is telling us shape. And so ideally, you might want to redraw this just to emphasize the 3D structure. So again, kind of looks tetrahedral, except instead of having, right, an atom on top, we've just replaced it with a lone pair here. So that looks pretty good. And so, right, all these group 5 typically kind of make this sort of thing so we can have phosphine. So again, it would have that lone pair. PCl3 is another example. Arsenic trihydride, or tribromide, etc. So we could go crazy. And so now this is kind of touching on expanded octets for a second, but so let's look at PCl3. So it looks like that. And so if we look at phosphorus trichloride, let's read it and then we can figure out why it is like this. So if you've ever worked with phosphorus trichloride, which you wouldn't, but it's basically a colorless, clear, angry fuming liquid, and it smells. And so why it's so angry is because it has this lone pair, right? And then this lone pair means it's pretty reactive. And so that means it wants to react with the water and the oxygen in the atmosphere, and basically likes to make a bunch of oxides. So plus oxygen gives us this compound. And this could be with chlorines, with H's. So phosphine, this compound, is also extremely reactive. So same concept. So this phosphorus is pretty sterically unhindered, or pretty naked with just little hydrogens surrounding it. Same thing with these little chlorines. And then that makes it really angry and reactive and fuming. And so it would go ahead and eventually react with oxygen to make this compound. And by eventually, I mean pretty rapidly. So you would see that. So that's why it would be angry, because it's literally making that as you use it. And if you were using this like a crazy person in a reaction, then you have to use like an air-free atmosphere and do all that, which I have done personally and do not recommend working with PCl3. All right, but that's a good hint. So, right, this tells us what it looks like and then gives us a hint as to how it will react. And then again, so this is, now phosphorus is considered hypervalent here. So we'll talk more about hypervalent. But basically, anytime something is hypervalent, it has more than 8 electrons at least surrounding it. And so right, how this is drawn formally. So how many electrons is phosphorus feeling in this structure? So check again. Count again, because remember each line has 2 electrons. And then, right, these are aligned, this is a line. 10, yeah. So don't let that double bond trick you. But yes, phosphorus is then feeling 10 electrons, so hypervalent, but can happen. Questions so far? Oh, and then just to be clear, so on geometry, so right now we have phosphorus back here with 3 things, or stuck to 1, 2, 3, 4 things. So once it reacts back with oxygen, right, this is tetrahedral again at its core. So just kind of watch that. All right, so let's look at group 6, and so we can see the pattern that they make. So what's our probably typical group 6 compound? Any guesses? And we're done overthink it. What's in group 6? What would be a good compound to look at? Probably one you use all the time. So oxygen's a good one, and then what compound is it in that we use all the time? Water. So good old water. And so let's just draw that. And so emphasize your lone pairs. And so now we can follow along on our chart. So this is 1, 2, 3, 4 things attached to it. So 2 bonding pairs, 2 lone pairs. Oops, 2 lone pairs. And so, that puts us under big group 4. And then we go over to this bent here. And so, yes, that's our geometry, is bent. And then we could draw, actually we want to draw 2 analogs. So we can also draw CO2. And then if we just draw on down the line, so we go sulfur, and just drawing out, so I'm drawing the same thing, so drawing it similar to water. So dihydrogen sulfide. So of course, similar geometry, still bent. We can draw it for carbon, how it reacts. So again, makes the same sort of analog. Oops. All right, so this is CS2 carbon disulfide. And so then going down the line, so selenium would do the same thing. So similar structures, selenium. And we can make this chloride too, so you could see that. Or any sort of halogens usually. And then this is also cool because it can kind of tell you why substances might be dangerous. And so what do you know about CO2? How is that related to human metabolism? What do you do with CO2 as a gas? You breathe it out. So it's a waste product. We breathe it out. And so now let's talk about CS2. So CS2, it's lower on the periodic table. So that already means it's heavier. And so this is still a gas, but it's a heavy gas. It's dense. And then the other issue is, so do you guys know how your little hemoglobin works? So you have, your iron hemoglobin. It starts off in your lungs with an oxygen molecule attached to it, It floats down to your leg or whatever, drops off the oxygen, picks back up CO2, and then, once you get back to the lungs, it disassociates CO2, again, as a waste product. But then CS2, if you were to breathe this in, it actually binds a little bit stronger to your hemoglobin than the CO2. And then again, it is a dense gas, so trying to exhale it is not very good. So yeah, you don't want to be exposed to large amounts of that. And then if you do, you have to be monitor your O2 levels, and then you might feel the next day you had a hangover or something if you're exposed to a small amount.
So oxygen has 6 valence electrons, makes it in group 6, but bent is a shape in group. Or is it just?
Well, so bent is a shape in 3. We'll come back to this, but this is how many things are attached to it. So this group is, so we're at group 2 here. Oh, sorry, 4, because we're at 4 because we have 2 lone pairs and then 2 bonding pairs. So that puts it in group 4 down over here on the bent. So on that note, let's try another typical compound. So this is a weird one, but see what you can do with it. So SO2, so how can you draw it? And don't make like a little circle. So don't make a ring, but what else could you do with it? Do you have a structure for SO2? I'm going to grab a marker so somebody can put on the board. Anybody want to put SO2 on the board? No volunteers? Elizabeth, do you want to go for it? Answer? It's fine if you are. Yeah, put it up on the far board. Hopefully these markers function. Okay, I like this idea. How many total electrons should you have in there? we can help her out too. So how many do we have, right? What did you say? So 18 electrons. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I think you have just, I would take it from the sulfur, because sulfur is already pretty hypervalent. Yep, so that looks good. Excellent. And so that was a good approach. So again, I'm not sure how exactly everybody got there. You can start off, just kind of drawing a line to each one, and then you start kind of playing around. So we know we have 18 electrons total. And so yes, the best structure is eventually you get 2 double bonds. So you could have started off right with a bunch of single bonds, and then you probably had to do some sharing to try to get sulfur satisfied there. Did anybody have anything else drawn with 18 electrons? And so now let's look at this one, because I wanted to talk about this one. So what big group number is it part of? Or like on this electron pair number. So how many things is sulfur attached to? So 3. So good job, right? So we have the lone pair is 1, and then 2, 3. And I'm kind of going back to Dallas's question now. And so this is a different bent. So now we're at the 3 electron pair. So notice we only have 1 lone pair. And so we're on that line, then this is actually a different bent. So there's kind of 2 bents. And so notice this one does not have the same angle as our traditional kind of bent water structure. This one, so the chart lists the angle. And so let's first write it. So the standard, and all I mean by standard is like we always talk about it. So this is our usual bent structure. So this is about 104.5 degrees. Again, right, those 2 lone pairs are kind of pushing them close together. And then just comparing this, so again, our group 3 here, and we'll put 1 lone pair, 2 bonding pairs. This gives us still bent geometry, but sometimes you may see this referred to as like V-shaped bent or something different as kind of a distinction. And again, you notice the angle is a lot larger, so it's just shy of 120, which would make sense, right? So 120, if it was a perfect thirds, it would be 120 exactly. But then the lone pair occupies a little bit more space, so it pushes them a little bit closer together of 119. Actually, I'm going to rewrite that as 119 degrees, just so we see that. So I just wanted to point that out, since there are 2 bents on there that could be confusing. And then this is kind of your classic example of the weird bent. And so then let's look at least the group 7 kind of normals, and we'll talk about more expanded weird octets and stuff. So group 7, again, usually we just expect them to make 1 bond normally. We'll look at some compounds with just like halogens. So like I4 is a compound, but we'll look at that later. And so again, right, group 7, just normally 1 bond to each other. And so I'm just showing silicon tetrachloride again, just to show those chlorines making 1 bond. All right, so let's get into some weird stuff. And so let's start with the noble gases. And actually, let's just start off with, well, how are they able to do this expanded octet? And so most of this is just due to it being physically larger. And so often you see kind of expanded octets once you get past the third row. And then I do want to point out this. What is that?
It's like a fully twisted up antler. It's pretty
I swear the weirdest stuff happens in like this classroom. Oh, you're right. It's just some guy blowing a horn. That is so weird. Okay. Anyways, so oftentimes, especially in like textbooks that you may have read or been familiar with, or even like your teacher, they probably say something of like, oh, that's because we need d orbitals to do these expanded octets. And that's actually wrong. So we do not need d orbitals. I won't go into why. So the whole why exactly goes into more of like an MO derivation. And I didn't want to do that because that's kind of too much for this class. But we can think about it kind of more simply. And so let's go back to the noble gases. And so let's start with xenon. And so xenon does some cool stuff. So xenon so we can have xenon difluoride or xenon tetrafluoride as two compounds. And so kind of my trick too, so notice, right, noble gases, of course they have 8 valence electrons. And well, if I take 2 of them to involve in bonding, so there goes 2. Then that leaves me with 6. So 1, 2, 3, 4, 5, 6. So then that gives me the picture there. And then I just fill in the electrons for fluorine. And so you could double check yourself with this picture. So we have 8 electrons from xenon and then 14 from fluorine. So what does that bring us to? Can't do simple math today. So 14 plus 8, sorry. 22, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So that looks good there. So see if you can draw the structure for xenon tetrafluoride then. And we'll keep talking about this. We have a structure. Someone want to put it on the board for us? Let's see. Sadie or Dallas, you want to do it? No. Still working. Who else wants to be my next victim? Ashley, what do you have drawn back there? Well, let's just put it on the board first, because it's actually not tetrahedral, but it probably has like 4 things attached to it there. And then a lot of electrons, right? Yeah, just, even if it's wrong, we can fix it. We just need a starting point. So it looks like you started off xenon. Hang on, let me look before you run away. And so how many total electrons is that, slash how many should we have though? So we have, right, 8 with our xenon plus 7 times 4. So how many is that? So 36. And so you have it drawn, so you just filled in the octet rule, which is a good start, right? So we're here. So let's just get to here. And then, so this is 32, right? So this is 1, 2, 3, 4, 5, 6, 7, 8. So each one of these is 8. So 8 times 4 is 32. But, yep. So then, yeah, exactly. If you're short, then put them back on xenon. So 32, 33, 34, 35, 36. So then it should look like this. So excellent job there. And so now we can figure out its geometry. And so it has 6 things attached to it. Right? So then it's this 6 electron pair group. So 4 bonding pairs, 2 lone pairs. So what geometry does that match up with on our little chart? You gotta look 6 electron pairs. Yeah, square planar, exactly. So then this matches with our square planar. And so this would kind of look like your lone pairs up and down in the plane of the board, and then your fluorines all coming out at us. I could redraw that. Do you have a question?
We did that, but we didn't pair them. And in nitrogen, we had the option to pair and didn't. Was it just, because pairing takes energy. So how do we know when to do it and when to leave it?
Like, so did you make double bonds or something funky?
Single.
But then, because were you short an electron or what happened?
We just didn't pair them, like we had 4, we still had 4 around.
One on each side.
I guess I'm just confused.
Around zero.
Because did you start like this, a bond to each? Because then once you get there, then people usually kind of fill in the octet next, or at least that's something that you might want to do.
The only issue is the pairing of the 4 remaining electrons in xenon.
So just what to do with them and how you knew.
How to know when to pair them.
Yeah, so the reason why we didn't like double bond them or anything, because maybe this was your question, is like how come we didn't put it into a double bond?
Sure. How to format them, because it's a little bit different.
Yeah, so then this one wouldn't work out as nicely because now fluorine would have an expanded octet. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that starts to get a little awkward. So if you're going to give anybody the extra electrons, you want it to be your larger atom so you can like physically hold them.
But you're saying you had like 1 on in between each single bond, or in between.
Oh, that you just had like 1 electron like that? It's because, yeah, they want to typically pair then.
Right.
Yeah.
But when it's even though, not, because we didn't do that in nitrogen, we had 3, we could have made another bond, but we did triple instead.
Yeah. And nitrogen, because nitrogen, the problem with this too is you just don't have a lot of electrons to play with. So you only had 10, so this is like your only combo. Yeah. And so that's something that we'll practice with. And we'll look at formal charges, not today, but maybe Wednesday. And that's like another way to just help us analyze our structures and figure out how to draw them. All right, let's go back to neon for a second. So these xenon compounds are pretty well characterized. You could also go crazy. So they have xenon, hexafluoride. But I did at least want to touch back on why I said you don't need d orbitals. And so that's because there's slowly mounting evidence that this compound might exist, or at least at a fleeting state. And so really the issue with neon fitting 5 fluorines around it has nothing to do with its d orbitals or lack thereof, but rather it's just physically small. So neon is just so tiny. So for this to happen, what people are noticing is that these two fluorines are more elongated bonds. But it's still there. So again, this is a pretty transitory species. They're still trying to like nail it down, but yes, there's evidence that neon and fluorine do react, and so the only way to for this to happen is kind of do this sort of structure. So yes, it can do expanded octets. So we'll, again, very transitional. So still being studied. And so let's look at more octets as well, and we'll keep kind of practicing and playing with this. And so we can look at other expanded octets. So phosphorus is really good at doing expanded octets. So phosphorus pentachloride or phosphorus pentafluoride are other combinations. So see if you can draw, let's do PF5. So see if you can draw PF5. What does that look like? And then if you get done with PF5, and you can also try SF6. And I'm just going to run to the bathroom real quick, and we'll go over this.
I don't know why I thought that, but I did. I'm sorry, I'm really bad with things. Don't take it personally.
Okay.
Okay, good.
What is that?
That's cool. And then my second guess was Aiden.
I mean, that is kind of people with me.
30.
40.
Aiden? Where are you getting 8 from?
It's an octet.
No, it's not.
It looks like a starfish.
No, it's 6 times 5.
Why is there 6?
Because it has 6 valence electrons.
What has 6?
What?
What do you mean?
He had 5.
What has 6?
P. Oh, wait, no.
No, yes.
F.
That has 7.
No, it doesn't. 1, 2, 3, 4, 5. Yeah.
You're
right. But that would be 35, not 40.
You have to add the 5.
Okay, I see what you're doing. You should be my tutor instead of the random person I hired.
So it's PF5. Phosphorus has 1, 2, 3, 4, 5. Fluorine? How is there more?
Wait, I think I got it.
The bonds themselves have,
As the tip. Yeah.
that's 4.
That's how I did.
so what do we get here? So did we get PF5, looks something like this maybe? And of course, I'm just drawing it in 3D already. But no expanded octet. So how many total electrons does phosphorus feel in this structure?
40.
Just the,
Oh, just phosphorus.
yeah, so not the total
35.
electron count. Wow, just what it's feeling. 5 bonds, but 5 times 2 is 10. Got there eventually.
It took you a couple tries, but it's okay.
And so let's see, you're calculating total electrons for us. So 5 with phosphorus plus 7 times 5, right?
Yeah.
So you had what, 40 total?
Yep.
Excellent. And then, yeah, phosphorus, then we say, has 10 valence electrons that it feels here. And then if we had, oh, what's the geometry on this based off of our chart now? So 5 electron pairs. Yeah. So trigonal bipyramidal. And so, right, kind of looks like 2 pyramids. Bipyramidal. You can kind of see it's like the first one on our group 5. And then what did your SF6 look like? So SF6 should have looked pretty similar. Kind of this octahedral structure. And so we can get, so total electrons, somebody help me out, so 6 plus 7 times 6, what is that? 48. Then how many does sulfur feel? So remember, it's just feeling all these. 12. And 12 electrons on sulfur. And then don't forget all your lone pairs. All right, that's pretty good. Let's try one more for fun. So let's try IF3. how our structure's going. Lexi, do you have an answer up there? Yeah, throw it on the board for us so we can see what we're thinking here. Yeah, you could put it at the front board or the far board. Yeah, if you can draw it 3D, go for it. Yeah, that looks perfect. So that looks pretty nice. So how did you get there? Did you just kind of go for it, or?
Well, at first I did the three, and then it equals, so it's 28.
So let's see. Yeah, 7 times 4, so 28 electrons. So you just started with your lines, and of course filling in the octet rule. And then you found you had 2 extras, I guess, and then put them back on the iodine. So that looks really nice. Oops, sorry, drawing way too many. So other ways to think about it, right? Iodine has 7 valence electrons. If it's going to make 3 bonds, right, 7 minus 3 gives you 4 electrons left over. So those are the 4 lone pairs there. Just other ways to see it and think about it. Yeah, and then I heard you say the shape, and so that was T-shaped. So excellent in recognizing that. All right. Let's move on for now. So we'll do more practice. That's pretty good, so just kind of getting a sense of it. So we saw expanded octets. So again, a lot of phosphorus and sulfur. Oh, and then I forgot to mention, so does anybody know what SF6 is good for? Sulfur hexafluoride? Any fun things you can do with it now? So sulfur hexafluoride, so you know how if you like breathe in some helium and that makes your voice really squeaky? Well, sulfur hexafluoride does the opposite. So sulfur hexafluoride, right, it's heavier, so it's more dense than air. So if you breathe in a little sulfur hexafluoride, then you'll get a low voice. But always be careful when inhaling strange gases, of course. All right, so now let's formally go over how to name these compounds, but I think you've kind of gotten a sense of it already. And so now we're looking at nitrogen and oxygen. So basically all we're saying is there's a crap ton of combinations, right, of nitrogen and oxygen. So they could be 1 to 1, 1 to 2, 2 to 1, 2 to 3, 2 to 4, 2 to 5. Right, we saw that with our xenon, so we could have like 2 fluorines, 4 fluorines, there's even 6 fluorines. So how do we determine it, right? And so again, we're finding the same combination of elements can have different formulas. So we can't just use our good old like magnesium chloride like we could with our ionic compounds. And so with our molecular compounds, we can just use prefixes. And so our molecular compounds, we said those were 2 or more nonmetals. And so now we write the name of the element with the smallest group number first, so whichever one comes first on the periodic table. And if they're in the same group, write the element with the greatest row number first. And then prefixes are given to the element to indicate the number of atoms. And so the first one, so let's just take CO for example. So you only use the mono prefix in the second ending, right? So you don't say like monocarbon, monoxide. You just say carbon monoxide. And so again, we have our same prefixes, our di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. So let's see if you can name these then. So give it a whirl. So try those 3 on your own, and then we'll go over them. So let's start going over them. So you can just shout them out. So what do we get for A? What do we get? Oh, what's the, you got the triiodide, but what's the N? Yeah, nitrogen triiodide. And then what about B?
Phosphorus trichloride.
So phosphorus, and then what do we need? How
Oh,
many?
it's 5. I have pentafluoride.
Pentafluoride. And what about C here? What is the 4 prefix again? Here, we can scroll back up. Yeah, tetraphosphorus. Yeah. Decasulfide.
Would it for B, would it be pentafluoride or pentachloride? Because it was.
Oh. I don't know why I put pentachloride, sorry. got excited about fluorines for some reason. Any questions on naming? So it hopefully should feel a little simple, or at least simpler compared to those ionic compounds. And then, so this is, so we're all on the same page. So how do we figure out our formula mass, our molecular mass? And so this could either be for like one individual molecule or 1 mole. And so basically you can just add up all the molecular weights that are from your periodic table, and it either gives you the mass in AMU if you're talking about 1 molecule, or it gives it in grams per mole. So find me the mass of silicon tetrachloride there. Do we have answers? We can work through it. So let's just go through it. So let's start. So silicon, and your numbers could vary. So I try to at least give it at least most of what we had. So 28.086 plus, and then chlorine's mass is 35.45. And again, might have some discrepancies with rounding. So times 4. And so I get 169.9 roughly. Is that what other people got?
Yep.
So sounds good, just so we're all on the same page. And so again, that's either AMU, or if you're talking about a whole mole, then it's grams per mole. All right, that's probably a good stopping point for the day. So we'll just go back and kind of look over geometry again and kind of keep practicing with these structures so you feel really comfortable with them. All right, I'm going to go ahead and end this stream, so I'll see you Wednesday.